Welcome to today's webcast series presentation, Pyrawall, the most durable vegetated wall solution. My name is Beth Brooks, Director of Civil and Structural Engineer Media. Thank you for joining this webcast, which is sponsored by Propex Geo Solutions. Before we begin today's presentation, first, some general information about the webcast and the GoToWebcast platform. The views of the speakers and organizations participating in this webcast are their own and do not necessarily reflect those of Civil and Structural Engineer Media or its publisher, Zweig Group. If you have any technical difficulties while viewing this webcast, please submit questions or a brief explanation of your technical problem using the question tab on GoToWebinar control panel, and a representative will assist you. During the webcast, you can also submit questions to our speaker using the same question tab. Submit your questions at any time and we will try to answer as many as we can later in the webcast. Zweig Group encourages group learning for our events. If you are viewing the live webcast with a group on one registered person's computer, that person must complete and submit the multiple viewer registration form for the group in order for everyone to earn credit. Download the multiple viewer registration form from the Handouts tab on the control panel. Submission instructions are on the form. Viewers of archived webcasts must pass a quiz in order to download a certificate of completion. Today's presenter is Stan Miller. Stan Miller is a professor emeritus, Department of Civil Engineering, University of Idaho, and an independent engineering consultant. His work has focused on applied rock engineering, slope stabilization, geosynthetic reinforced earth structures, and erosion sediment control. Over the past 25 years, he has taught seminars on slope stabilization and segmental retaining walls in the US, Canada, and Southeast Asia. Since 2001, he has served as co-instructor for the ASCE Continuing Education Seminar on Soil and Rock Slope Stability, which is taught several times each year. He earned his BS and MS degrees in Geological Engineering from the University of Arizona and his PhD degree from the University of Wyoming. He is a licensed professional engineer in several Western states. And now I'm going to hand it over to you, Stan.
Thank you, Beth. Okay. All right, Beth, is that looking good?
Yes, it looks great, Stan.
Okay. Well, thank you all for joining today. I'm hoping to present an overview of this new technology from Propex. On this cover slide here, you can see the first trial wall that we constructed here on the left side several years ago in northern Georgia. And on the right side in this image, we're looking at a 17 to 18 foot high retaining wall that was used for a bridge approach embankment in Washington State. This wall was constructed last year. For the talk today, we're going to look at an overview and introduction, and I'm going to go through some typical applications of this technology. We're going to hit on the durability and longevity of the system, at least as we're projecting it. I'd like to include some historical background leading up to this new technology, and then some installation and construction overview and some guidelines. I want to briefly discuss the geotechnical design approach that's used for both retaining walls and reinforced soil slopes. And then I'll present a short case study and then summarize everything at the end. So, sorry about that. We're going to present design and construction examples for Pyrawall. It's a new geosynthetic system. I need to get rid of this screen over here so I can read my. There we go. Now I can read my slides. Okay, it's a new system for constructing vegetated retaining walls and reinforced soil slopes, and it relies on PYRAMAT 75, which is a high-performance turf reinforcement mat that's been available for over 20 years. But this mat is now used in conjunction with fiber composite internal braces to be able to stand up lifts and do a wrapped wall. This system requires no external temporary formwork or supports to place, fill, and compact the soil lifts, and no specialized construction equipment is needed. And often the on-site soil can be used for wall infill soil, providing significant savings. Now, that on-site soil obviously can't be an active clay or an elastic silt material. Over the past 45 years, we've really seen a revolution in the geotechnical industry. Horizontal reinforcing elements like steel strips, grids, geotextile fabrics, and polymeric geogrids have been used in compacted soil masses to construct what are known as mechanically stabilized earth structures. Now, Federal Highways has separated these structures into two categories, walls and reinforced soil slopes, the break coming at about 70 degrees. So structures that are steeper than 70 degrees are known as MSE walls. If they're flatter than 70 degrees, they're known as steepened reinforced soil slopes, or RSS. The face angles of these RSS structures typically range from about the angle of repose, 38 degrees, up to about 70 degrees. Now, as planners and designers and land developers have pursued living green alternatives to hardscape wall facings over the past few years, several viable systems have emerged, and these include the metal wireframe modular units at the face lined with some kind of a porous geofabric in the hopes that we can get vegetation to grow through them. And secondly, geotextile wrap face systems relying on a temporary form system that's inserted at each lift to provide a bulkhead against which to compact the backfill soil. Now, these wrap face systems have been around for a long time, 25, 30 years, but because the geotextiles used do not have durability or long-term UV resistance, often these wrap face structures were temporary, only used in construction to form like a crane pad or some other temporary feature, and then within a year or two, the structure is dismantled. That's going to change, or it is changing. Here's a typical example of a wireframe facing system with a wireframe face with metal struts, a geotextile liner filled with soil, and then vegetation hopefully growing through that whole face. In terms of the wrap face system, here's a photograph that shows a fairly significant wrap face structure. This particular one is going to be a permanent structure, not a temporary one. And we know that because we're seeing these weep holes put in PVC pipe, so they're eventually going to shotcrete this face and provide a permanent facing. Also, notice the temporary form system here at the top, where we're using temporary forms to do those wrap lifts. These traditional wrap face systems, some little sketches here from an old Federal Highways document. The geotextile wrap, a slip form is used. Sorry about that. A slip form is used to make the wall steeper. Regardless of either one of these two, they're typically in the past, they've been temporary because of lack of UV protection. Is there a poll question that pops up here pretty soon? I just got to ask.
I think so. We may.
Beth,
Yes, I will go ahead and release that right now. I've got 2 to release, and I'm going to release both of them right now.
okay, thank you.
And we're going to give the audience about 20 seconds to answer each one. Those are the results from the first one, and now here's the second one.
Okay, so getting back to this discussion on wrap face systems, regardless of what material was used here in the past, uh, there would have to be some kind of a permanent facial treatment in order to make these be permanent structures. And again, in the past, it's been some kind of an anchored high performance turf reinforcement mat or shotcrete or a boulder type facing to make these structures permanent. Now, just some typical applications here of a Pyrawall system or basically any MSE structure. You'd like to put in more usable flat ground, so you can put in a retaining wall to make flat ground above and below that to increase the usage of your property. Also to remediate slope failures by reconstructing the original slope to restore your desired grades. Oftentimes this is a roadway that's lost part of its fill, and the idea is to reconstruct the roadway and regain the shoulder that was lost. So another example of using a retaining wall system. Pyrawall provides an alternative for a modular block wall or a gabion wall where vegetation is preferred by either the owner or the client, and also for stream bank stabilization or repair. This is an example here, a photograph of a case study that I'm going to do here later in the webinar. Wetland, coastal, marine, or other corrosive or saltwater environments where designers want to avoid metal or concrete materials. Again, a little schematic drawing here showing a 1-to-1 slope of wrapped Pyrawall with sand infill, providing an option to vegetate and have an alternative to, say, large riprap. We can also provide a steep vegetated option for detention pond perimeters, levees, landfills, and other similar applications. Here again, that might be the case where a developer needs more flat ground or would like to be able to sell more property. So instead of constructing a detention pond with a 2-to-1 side slope, you can go much steeper than that, and again try to save the flat ground above and avoid any long-term mowing maintenance, because once this vegetation is planted, it pretty much is on its own. You may have to do some weed control, but you'll see a note here on rhizomatous grasses. This is what we typically recommend for a system like this, because these types of grasses spread through runners in the root system. So they will fill in bare spots and basically try to form a consistent, uniform vegetated surface. And then another example would be we're going to use soil nails, or in the case of a weathered rock system, it might be ground anchors where a steep face is required. So what would happen here is there's top-down construction as these soil nails or anchors are installed. And then once you've got a working bench here, if you want to have a vegetated face on that, instead of spraying shotcrete on it or stacking gabions up or something similar to that, you could come up with a 4-foot wide section of Pyrawall and get it vegetated. So what about the design life of this PYRAMAT? This PYRAMAT comes in both a green and a tan color. This PYRAMAT 75 is the heaviest such fabric that Propex produces. First of all, it has a tensile strength of 4,000 by 3,000 pounds per foot. That's a machine direction by cross machine direction. Has high UV stabilization up to a 75-year life if it's exposed. 90% is retained, the tensile strength is retained at 6,000 hours. And then appropriate applications for this PYRAMAT have been in high flow channels, steep slopes, severe non-hydraulic stress conditions, or, as we're going to talk about today, in Pyrawall. Some more additional information on PYRAMAT 75. Antioxidants are incorporated to increase the stability and durability. In the xenon arc testing, this is the ASTM procedure for looking at UV resistance. They accelerate the exposure, you get changes in temperature and moisture, and the tests, typically these tests are run to about 10,000 hours. The product has a good retained tensile strength, and of course, anytime you have lab tests, it'd be nice if you could correlate that with actual field performance. And Propex has a field site in Scottsdale, Arizona. 2002, the initial installation of the tan PYRAMAT. 2008, partially covered with growth. 2018, quite a bit of growth, but there are areas in that wash where it's been exposed to the sun. So here's an example of a photograph, 16 years of exposure. a third party took a sample of this fabric and tested it in wide width tensile strength, and over 80% of the original strength was retained. So Scottsdale is a pretty good test site, because looking at this national map, you can see down here in Arizona, we've got about as much solar radiation as we're going to get anywhere in the continental United States. In terms of functional longevity, you can take those xenon arc tests, plot them up here along with the Scottsdale information, and this provides this projected curve that takes us out to a functional use, the functional longevity at about 1,200 pounds per foot at the end of 75 years. So when ProPEX says 75 years, that's what we're talking about. Okay, can we do the next poll question now, Beth, please? That's the previous question, right? Beth, was there a third polling question at this point?
I believe that one was it. And then we have one more at the end.
Okay, well, we'll go on then. Thank you. So I just want to briefly talk about this functional longevity, because there's a lot of folks out there in the industry that look at plastics as a bad thing to put out there in the ground. But if that's the case, most people are thinking of these single-use plastics. There's a difference between engineered plastics and single-use plastics. And I prepared a little list here. Well, ProPEX provide a lot of this information. Engineered plastics, particularly the PYRAMAT that we're talking about, has a durable, it's comprised of a durable polypropylene that does not leach, and it resists generation of microplastics. In contrast, these single-use plastics are unstable polymers. They're cheap and inexpensive. They tend to leach and break down into various microplastics. Engineered plastics like PYRAMAT are stabilized to significantly reduce the UV and the chemical degradation. Not so with the single-use plastics. The engineered plastics are designed for long-lasting or permanent use up to 200 years in some applications, whereas the single-use plastics are discarded after single use, and they immediately begin to break down and degrade. These HPTRMs support natural environments by preventing erosion, promoting rapid root growth, and sustainable vegetation. In fact, these HPTRMs work together with vegetation to provide a permanent solution versus some kind of a biodegradable solution that may eventually fail. So they're very good for establishing permanent living shorelines and for maintaining cooler water temperatures than traditional hard armoring systems. And obviously the single-use plastics are not good for the environment. So just a little bit on the historical perspective. Back in 2000, there was a stream bank stabilization project that went in Washington State. A stream was eroding into a roadway, and the idea was to try to stabilize this and use a vegetated system rather than a bunch of riprap. So I've accelerated here past a bunch of the construction photos, but I wanted to show you they used a slip form system with PYRAMAT. At the time, the PYRAMAT was in the black color, and they basically used these lifts with a slip form with the PYRAMAT at the face, and then geogrid extended back into the slope. They constructed a reinforced soil slope at about a 1-to-1. They put live brush cuttings in between the lifts, hoping to get some vegetation established. And here's the completed reinforced soil slope later that same year of the construction. And then here's a Google image map from 2016 showing how the whole slope has been vegetated, and you can't even tell there's any geosynthetic materials involved there, but obviously they're doing the work in conjunction with the vegetation to permanently stabilize that river bank. So what about this new Pyrawall technology? Well, we're taking that PYRAMAT 75, using it as a face wrap. We're going to incorporate some internal braces that are composed of high-strength fiber composite materials, primarily nylon and fiberglass. They snap together to form a brace that stands up a 1-foot-high section of the PYRAMAT, allowing backfill soil to be placed and compacted. And then finally, for walls that are higher than 7 or 8 feet, you're going to need more than just the PYRAMAT wraps. You're going to need horizontal geosynthetic reinforcement, which could be a woven geotextile or a geogrid used in the reinforced backfill zone. So here's a typical schematic of what a Pyrawall would look like, where we've got the PYRAMAT wraps at the face. We've got geogrid extensions that come back and provide essentially the main holding power for this wall system. And you can see the internal braces there. Really, the internal braces could fall apart after 2 years. Nobody would really care because you've got the wraps and everything's tied together. All the bracing is used for is to provide a way to fill up those wrap lifts and to construct the wall. So another option for installing the geogrid, and we've had feedback from contractors over the first year and a half that have helped us, come up with this concept. They say rather than sandwiching the grid in between the lifts, if we're doing 6-inch compacted lifts to get these 1-foot wraps, it'd be quicker for us to just compact the 6-inch lift, put the grid in, then put the next 6-inch lift on, and then we won't have to be putting soil on top and bottom of the geogrids and in between these wraps. So this is an option if the contractor is using 6-inch lifts. Now we've had projects where the contractor had heavy equipment and they were actually compacting in 12-inch lifts. And when you're compacting in 12-inch lifts, then of course the better way to do it is to put the geogrid sandwiched in between the lifts. Here's a typical reinforced soil slope. It's at a 1 1/4 to vertical to 1 horizontal, so that's about 52 degrees. And again, in this case, you can see some topsoils being placed at the face. We've got these long primary reinforcements, and then the Pyrawall itself, or the PYRAMAT, provides a secondary reinforcement at the face. Typically, these reinforcing layers are at a maximum 2-foot vertical spacing. And when you do the overall global stability analysis for a wall like this, what you often find is you need to put extra layers and longer geogrid layers at the base in order to force potential failure circles to go deeper and thus increase your factor of safety. So it's not uncommon to see a system like this with geogrids and then have a section near the bottom that may have longer and stronger geogrids. So typical on-site preparation would involve constructing a working platform or a trench, and then allowing a flat base to begin construction on. If you have clay or elastic silt subgrade materials, you'll probably want to put in a granular or gravel base that's compacted with a drainage system. In this case, I've got this geotextile fabric, a filter fabric wrapped around the drainage pipe and providing separation between the gravel and the clay subgrade. In terms of a final grade that's going to not be horizontal, we're going to have to step this system just like you would a modular block wall. If you're dealing with 8-inch high modular blocks, you're going to have to step the foundation on 8-inch increments. With this 12-inch PYRAMAT lift, you do the same thing, except those steps are going to be on 1-foot increments. Also in plan view, you can construct curves with this PYRAMAT fabric by cutting the fabric, both bottom and top lifts. The cut is made to within 3 or 4 inches of the face. If you're doing an outside curve, you cut and overlap the fabric. If you're doing an inside curve, you cut and spread the fabric. And the minimum radius of curvature that we've found out in the field is about 6 feet. So this internally braced wrap face system relies on these composite bars. And to install these, a lower bar is threaded through, a fold line is marked here where 4 feet of the fabric will be on the base, 1 foot of the fabric is in the upright, and then 3.5 feet is extended back for the top wrap. That brings us to the PYRAMAT roll itself is 8.5 feet wide by 120 feet long. So one of the advantages of this system is when you roll out a roll of fabric, the full 120 feet, you're going to construct that full 120 feet at once, and you're not going to be having multiple back wraps if everything was in the roll width direction, such as a 10-foot wide roll or 12-foot wide roll, and you're going perpendicular to the face. We're actually going parallel to the face with this PYRAMAT roll. So we then level the subgrade, compact and proof roll it. We install the internal braces and place the first lift of the PYRAMAT. And by the way, anchor pins, usually they're 9 or 12-inch steel pins, are used to anchor this along the proper line and to stretch the fabric, and then pins are used at the back. We backfill with soil in order to get it compacted. We can compact the soil near the face with small equipment. Usually just a vibratory plate compactor is used right near the face. You can also use a jumping jack compactor within about a foot of the face. And in the case of large embankments, you're going to probably have a 12 or 15 ton vibratory roller that's going to be compacting in 12-inch lifts. And in that case, you're probably within 32 or 36 inches of the face with that heavy roller, and you're using the smaller equipment near the face. So once you get that lift compacted to the full lift height and you check the grade, you pull the top flap back on the fabric, and you pin it, stretch it fairly taut and pin it, scatter a loose layer of soil on that top lift, and then place the next lift. You just keep repeating this process till you build up the wall. Now, when you have rolls that meet end to end, we basically just take a brace and install it right at the end of the fabric to be extended. We shingle the joints so that if there's water flow direction or a preferential wind direction, you want to make sure that we're shingling so that the extended one fits inside in terms of the way this drawing shows. So this braced PYRAMAT lift is then just, sorry about that, is just slid in and butted up against this other brace in that particular roll. Now, if we're going to add topsoil at the face, we follow these basic steps. We use our structural fill. Normally, the loose lift height is going to be 7 or 8 inches because we're going to compact it down to 6. If you're going to be putting topsoil at the face, we like to taper this off a little bit. We want to get some structural fill around the braces, get that lift compacted. Second thing is to put in your topsoil little triangle there so we can get vegetation to grow. Add the third lift, and before we pull the top wrap back, we want to make sure that we've got our seeding done. So we scatter seeds, either grass or forb seeds, on the top of this topsoil layer, and then we pull the fabric back and pin it. We can add sprigs or bare root plants in between the lifts or directly through small holes cut in the PYRAMAT. So just a quick look here at what these vegetated features look like. This is our trial wall in northern Georgia after it was constructed in 2014. All we did was scatter a little bit of seed, before we pulled the wrap back. This was what it looked like 2 years later, and then a recent photograph shows you can't even hardly tell that trial wall is even there, because not only has the grass grown well, but a lot of volunteer vegetation has come in there as well. Now, for post seeding, again, you can sprig live roots through that fabric, or you could actually hydroseed on this face, and you'd be able to get vegetation growing on these little steps, in between the lifts. This is the project in Washington State. Again, this was completed last October, so this is the first signs of growth this spring. See the grass coming through on the lifts, and then pretty good overall vegetation cover on this embankment. So as far as engineering design, what's the basic things we need to address here with this Pyrawall system? If we're designing walls, we're going to follow the general procedure for allowable stress design, where we're going to look at base sliding, overturning, bearing capacity, and overall global stability. So these drawings are from NCMA for modular block walls, but the same approach works for the Pyrawall. Typical factor safety design criteria is shown here, where we're looking for minimum factor safety of 1.5 for base sliding and bearing capacity, and a minimum of 2.0 for overturning. And then global stability will be from 1.3 to 1.5, depending on how critical the structure is. In terms of internal failure modes, we worry about pullout and rupture of the grids, but believe it or not, over the last 30 years, what we've come to realize in these geogrid reinforced retaining wall systems is that if we get adequate embedment length for our geogrids, the problem's not going to be pullout. We're actually going to see the grids rupture before they pull out. So we're really looking at geogrid rupture in terms of design criteria. And what about that rupture? What's our design criteria? Well, it's the long-term design strength of these geogrids or these woven geotextile fabrics. Used to, manufacturers would provide you with these reduction factors for creep, installation damage, and environmental degradation, and you'd have to calculate the LTDS. But in the last 4 or 5 years, manufacturers have just started publishing the LTDS numbers on their website. So you can get on any geogrid manufacturer and they're going to have their LTDS for their different weight of grids. Once we know what the T allowable is going to be, once we do our calculations, we're going to multiply that by a factor of safety 1.5, and that's going to tell us that our long-term design strength is going to have to be greater than or equal than that T allowable times 1.5. So the basic calculations involved with engineering analysis rely on this Coulomb active earth pressure coefficient. It's a big equation, but it's in all the literature from the 1980s on, where we were dealing with these geogrid reinforced walls. In this notation, the beta is the batter angle of the wall. The phi is, of course, the friction angle of the retained soil. And then phi sub W is the friction angle of the wall soil interface. For modular block walls, that's traditionally been 2/3 of the friction angle of the retained soil. But if we don't have blocks, if we're just going to have wrap layers, that the interface friction angle is usually up to about a 0.85 of the friction angle. And then U, of course, is the back slope angle above the wall. So the force that we really have to counteract with the grid system is this F sub A. It's what I call the lateral earth pressure force. This will be in units of pounds per running foot or kilonewtons per running meter along the wall face. So after we do the calculations for the internal and the external as far as the base sliding, overturning, bury capacity, we also have to look at the possibility we'll be designing a reinforced soil slope rather than a wall. So with these reinforced soil slope structures, because they have a much higher batter angle, we're looking at a 20-degree batter angle or more from the face, then the primary design approach that we want to do is based on the global stability. So we've got two options with global stability. The critical failure circle is outside of the reinforced zone, and we want to make sure we can meet that factor of safety. And then secondly, we deal with compound stability, where there may be a critical failure path that actually goes through the grid zone, ruptures those grids. That has to be analyzed as well. So with these reinforced soil slopes, we essentially do a method of slices where we're looking at failures outside the reinforced zone and failures that may go through the reinforced zone. So for walls, we're looking at base sliding, overturning, bearing capacity, and global stability. For reinforced soil slopes, it's all a global type stability, but we have to look at both the large scale and the compound stability where the failure path can go through the reinforced zone. So a case study, just like to go through this case study fairly quickly. This is a Pyrawall that was average height of about 7 feet. There was a few zones that were 8 feet high, some were 6 feet high. It's a stream bank stabilization project. So because of its limited height, there was no geogrid extension involved here. We're just relying on the PYRAMAT itself for the reinforcement. This was completed last year along the Kaneohe stream in Kaneohe, Oahu. The city and county of Honolulu preferred a soft, more natural reinforced vegetated system, in contrast to the concrete lining that you can see here on the other side of the channel. In fact, that historic concrete lining is probably the reason that they had such terrible erosion problems on this other side of the stream, and people started to lose their backyards. Pyrawall was selected for this 330-foot long repair zone. So just a quick location map. Kaneohe is on the east shore of Oahu. Here's Pearl Harbor. Here's Honolulu and Waikiki. There's Kaneohe Bay. And the stream basically flows northward, then makes a little bend and flows into the bay, generally eastwardly. So over the past 30 years, high flow events in the stream have eroded the eastern side of the channel. Again, they've got concrete on the west side, and the eastern side started to take a beating, and people started losing their backyards. Here's a site plan, and I've got the 3 test pit locations circled there. I had to kind of tip this a little bit to keep my north arrow going up the page, but here's the repair section. We got 3 hand dug test pits. Access to this site was basically zero. There was no way to get equipment in there because of the houses. Eventually, I mean, when they actually built this structure, they could get a small little track hoe in there and very small equipment. And basically for fill material, they had to use a conveyor system and convey soil from a side yard out in the cul-de-sac back to the location. So very limited access here on this project. Here's a sample cross section. This shows an 8-foot high section of the Pyrawall. The landscape designer wanted to include a planting bench partway up the slope. So that's why there's this little setback here. So in terms of the site investigation and testing, we had 3 hand dug test pits. The depth went to a maximum of almost 4 feet. We collected disturbed bag samples and undisturbed 2.5-inch diameter driven tube samples of the on-site soils. We described site topography, general surface and runoff conditions. And then during initial excavation, the geotech engineer of record wanted to have bag samples collected in order to do the modified Proctor test in order for compaction control. So here's an example test pit log, this typical geotechnical log. Notice that we're dealing with a silty sand here with some gravel. So it actually made a pretty good structural backfill material. Particle size analysis from test pit 3. Notice again, we've got a silty sand. There are quite a bit of fines in here, and those fines tend to be somewhat plastic. This was one of the bags grabbed at initial excavation. Again, a silty sand, but notice the liquid limit and the plastic limit. These tend to be fairly high numbers for what we'd like to see in a backfill soil, but the soil was approved. And here's a direct shear test. We're getting a friction angle of about 31 degrees. This sample again was from test pit 3. So we have a working friction angle. We're going to need that. And here's a modified Proctor test, ASTMD 1557. And notice that the maximum dry density is around 88, 89 pounds per cubic foot, but the optimum moisture content's in the order of 31%. So there is some clay in this material. And at that high of a moisture content, we had to really make sure during construction that the contractor was taking care and not trying to compact the soil when it got too wet. So we went through the basic geotechnical analysis. The stability analysis results for the 8-foot high wall section with the overall batter of one vertical to, or it should be one vertical, sorry, little typo there. It's 1 to 3 vertical or 71.5 degrees. These are the computed factors of safety for base sliding, overturning, bearing capacity, and for global stability. And in terms of the recommended minimum LTDS for the geogrid, 530 pounds per foot, which is not a whole lot. This is to be a fairly light material, and the PYRAMAT itself easily meets that. So just a quick look at the global stability analysis. There's our wall with the planning bench. Here's the calculation of the factor of safety, and it came up at 1.68. So in terms of construction, the subgrade is leveled and proof rolled. First layer of PYRAMAT goes in. Filling around the braces is the best way to go here to prevent, putting soil in between the braces and popping out, and then the braces tend to lean. We always want to fill in around the braces first, as shown. compact a 6-inch lift, then compact the extra 6-inch lift to get our 12-foot lift height. First wrap done, soil added to the top, second wrap lift placed, and on and on and on till we get to the full 8-foot height. And then the vegetation was added. In this particular project, no grass seed was used in the internal wraps. All the vegetation was applied afterwards, so post-construction. There were 3 species of vegetation that went in. There was a grass that went in near the toe of the slope. Then there were 2 different, well, a woody shrub was planted on the planting bench, and then on top it was a creeper, some kind of a vine creeper was planted along the top of the wall, and that's what's shown along here. So when the project was completed, there's the Pyrawall. Again, the concrete on this shoreline versus the Pyrawall on that shoreline. And my guess would be within a year, being Hawaii and how everything grows there, this wall will be entirely covered with vegetation. So in summary, this Pyrawall is an internally braced geosynthetic wrap face system, allows relatively easy construction of a durable vegetated MSE wall or reinforced soil slope. There are no metal or concrete components used in Pyrawall. There are no external temporary forms or bracing needed to make these soil lifts and to build the wall up. In many cases, on-site soil can be used for the infill, given it contains very little organics and it's not an elastic, fine-grained soil. Straight or curved alignments are possible. The slope angles that we generally recommend for Pyrawall are going to range from about 51 to 76 degrees. When you start getting flatter than this 51 degrees, you're probably looking at a more economical solution to use Propex's ArmorMax system, which is essentially it's an armored vegetation system with anchors, and you basically prep the slope, grade the slope, put any seeding or topsoil on it, and then roll out the PYRAMAT and use percussion-driven anchors directly on the slope. That's probably the preferred treatment when you get much flatter than 51 degrees. And remember that federal highways has the break at walls are steeper than 70 degrees and reinforced soil slopes are flatter than 70 degrees. This system's well suited to wetlands, shorelines, or saltwater areas due to environmentally inert and durable components. Essentially, we could do here is provide an engineered permanent shoreline. There's no biodegradable materials here that can fall apart. If you're doing a repair in the first place, it tends to indicate that vegetation alone was not strong enough to maintain that shoreline. So the Pyrawall, in conjunction with vegetation, could provide an engineered permanent shoreline and not have to worry about a biodegradable system that you're back in there fixing, 6 or 8 years after you installed it. Vegetation can be seeded or planted during placement of individual soil lifts or post-construction by hydroseeding and by transplanting sprigs or bare root plants through the fabric. One of the nice things about this PYRAMAT is that it's knotted at each of the connections, so you can punch a small hole in it, sprig the plant in, and there's not a concern about this fabric unraveling because it is tied and knotted at every connection. So again, this wall that was constructed last year in Washington State, the vegetation's coming in well, and I guess Beth will open it up now for questions. That's my presentation. Thank you.
Thank you, Stan. I think at this time, Drew is going to take over on the Q&A part. Drew?
Awesome, thank you. So guys, we have a good amount of questions that have come through. What I'm going to do, I'm just going to read through them one at a time and answer them as we can. If I misunderstand your question or don't address it as much as you'd like, feel free to submit another question to clarify. So the first question was about the retained tensile strength of the PYRAMAT 75. The question was, is 80% with 80% tensile strength retained, is there any statistics associated with it? So I will say, as a manufacturer of the PYRAMAT, we have a very stringent quality control testing procedure that tests the material very, very frequently. So there's a lot of data behind the understanding of what the baseline tensile strength is. We then, on top of that, have done a significant amount of testing from field samples, and we do that testing pretty consistently. So every year or two, we go back to the same site and get more tests. Each time we get about 5 samples and do about 5 tests per sample, so about 25 test results to try to get us at least a good confidence of the values we get. So for the next question, the question is Pyrawall feasible for sites with smaller footprints and steep slopes with a low batter? So I would say when you have a smaller footprint, Pyrawall is an option. The minimum batter we go to is around 14 degrees. So there is a limitation there on that side of it. But depending on scenario, we can definitely look at that. Every scenario is a little different. Each project is unique with soils and geometries that are specific for that project. But we can definitely look at those scenarios as needed.
Drew, if I can add a comment in on that. Not only that 14 degrees is a 76-degree slope angle. And what that means is that we have to have a little bit of a step on each one of these lifts. And if we could probably go steeper than that mechanically, but my feeling is, and I've talked to other folks here, it's going to be very difficult to vegetate something that's much steeper than about 1/4 to 1 or 76 degrees. Thank you.
Yep. So the next question, is it necessary to use drainage media to fill the PYRAMAT wrap? So in case of a water ingress, will the soil clog the PYRAMAT and build hydrostatic pressure or head? So a good question. Depending on scenario, we've looked at using different infill material. If it's truly a wall application where there's no water present, we can use a soil that is, whether it's on-site soil, if it's suitable. But in other areas where we have more of a shoreline application, using a more freely draining material, whether it's a 57 stone or a sandy soil, that would help a lot with drainage. And really, there is really no potential for that PYRAMAT to clog. While it is technically a geotextile, it's not like your common woven or non-woven geotextile. It has about 10% light penetration, which means that it really drains freely and doesn't build up any of that hydrostatic pressure. The next question is, so how do you backfill around the braces? I think this was a little bit addressed in Stan's presentation. When we get to the braces, usually that's the part you infill first, using a shovel or your hands just to place the soil around those braces first and compact it as well. Once the soil is placed there first, then you can place it around the rest of the area. Next question, is there a compaction specification? So we typically say at minimum 85% compaction is what we want to achieve modified Proctor. But depending on the scenario, we can look at higher compaction requirements.
If I can chip in there, this project in Washington State, obviously this is a road embankment approach to a bridge, and the specification there for the fill was 95% modified Proctor, which is pretty standard for highway embankments. Obviously, you can't get 95% when you're within a foot of the face, but within 2 feet of the face, you can pretty much get 95%. Generally, that was a very good structural fill material with a lot of good granular material in it, so they could achieve that fairly easily. The Hawaii project, on the other hand, I don't think there'd be any way there they could have got 95% of a modified Proctor, but it wasn't a road embankment, it was a stream bank. So I just say, depending on the site and what the requirements are, if the geotech engineer specifies the correct kind of fill and the contractor has the right kind of equipment, you can pretty much meet a standard spec, whether it's 85% or 95% of modified Proctor.
Okay. Next question is, can Pyrawall be applied in a Canadian climate where the majority of the time it's winter and cold and you only have about 2 months of summer to get vegetation to establish? So in general, yes, it definitely can be. We've done a lot of work with the PYRAMAT material in Canada in various applications, so there's not a durability concern. In terms of the vegetation establishment, I would say it's probably more critical when there's a hydraulic component to it, if there's an erosion issue potential. If vegetation can't be established, you can always use, as I mentioned before, a different infill material like a 57 stone, something that can be there and not have any potential for erosion and essentially be intentionally used so that vegetation won't establish. The durability of the PYRAMAT is sufficient even without vegetation to provide the long design life that we need. Next question is essentially with there not being any framework in the face, how do you control deformation? And along with that is how high can you go with the Pyrawall system? So the internal framework, the bracings really help control the deformation on the front side of it, where you're putting those on 2-foot centers to minimize that deformation on the face. It is a flexible system, so it's designed to be able to accommodate any deformation that does occur. In terms of the wall height, we've gone up to around 18 feet tall so far with additional primary reinforcement. And that's, to be honest, is really a function of the geotechnical stability of the wall itself and the holistic design, not necessarily just the Pyrawall component of it.
I'll chip in again here. I could see reinforced soil slopes going, 50, 60, 70 feet high, because you're really relying on the primary reinforcement of the geogrid layers. And in that case, the Pyrawall structure at the face is providing the erosion protection and the ability to try to get that slope vegetated. So yeah, there's probably no actual limit to the height of these systems, because it'd be just like any other geogrid reinforced system. If you got the grids in there and you've got the soil properties and you've done your global stability analysis, you could probably go as high as you can almost imagine. But I think from a practical standpoint, the steeper the wall face is, I mean, if we're looking at 1/4 to 1, I think the higher you go, the harder it gets to maintain line and grade. And because it is a flexible system, it's not like you're laying concrete blocks down. It will be harder and harder for the contractor to maintain line and grade once you get above about 15 or 20 feet in a steep Pyrawall system.
So the next question is, do you need to obtain soil data via soil borings? So with any geotechnical application, the more information we have, the better. You can always make assumptions, but those assumptions don't always pan out. So I'd say as much as possible, getting soil data is pretty critical, not just for the retained soil, but the infill material as well. Making sure that you have enough weight in that reinforced zone, make sure you have good interaction between the geogrids or the Pyrawall and the infill, and then making sure that the retained soil you have is what you assumed it to be. So the most information we can get, the better.
You don't always have to have borings. I mean, test pits are probably just as good if the wall's not going to be very high. The idea is a limited soil sampling and testing program, of course, is always going to be recommended for any retaining wall that you build. But most of the projects I've been involved with the last several years, we've been able to get the data we need from test pits and not have to do soil borings.
Next question is, will the slides be available after the presentation? If you can give us some more clarification on what information you're looking for, we can be happy to talk to you more and try to give you some more information. And we'll provide contact information. You can get with me, Drew Loazo, the Engineering Services Manager, and we can get you more information on that specific info. Next question, in areas with small footprints for horizontal reinforcement, can PYRAMAT alone work for both the face wrap and the reinforcement functions? Yes, it can, depending on the geometry and the potential for instability. As Stan presented, the Kaneohe project used solely Pyrawall for a decent sized wall, but again, it depends on the scenario. So if it gets to a point where you don't have more room to have any excavation, there are combinations of systems where we can use Pyrawall along with driven earth anchors to complement that if excavation is not possible. Next question, is there a limit to the size of vegetation that can be planted in or behind the Pyrawall? So not necessarily specific to Pyrawall, but specific to PYRAMAT, the high performance TRM that's used. We've had PYRAMAT for over 20 years, and we've used it in a slew of different applications, locations, and with a lot of various vegetations. I would say that with PYRAMAT, we've seen anything from just turf grass to more vines. We've also seen a lot of trees and small shrubs grow through the material. So while it might have some impact if you have a big tree growing through your wall from a stability perspective or from a maintenance perspective, it's not going to be inhibited by the PYRAMAT itself.
As Drew said, I think that if you're going to have large trees growing through this eventually, it might be a mechanical stability issue, but not necessarily a getting it to grow issue.
Right.
Another thing to mention, when it's been interesting working with landscape people and wildlife people on some of these projects, because an engineer doesn't view things like they do. For example, you don't want to plant anything on these highway embankments that are going to attract the deer or the elk or bears if you're in northwestern US. So the species that were selected, particularly for this wall in Washington, were done with that in mind. You don't want to attract wildlife to the roadside. So that's just another thing to throw in there as far as vegetation.
Next question is mentioned that saltwater or coastline reinforcement was stated in the presentation. So the question is, how does the performance, what is the performance against wave action? So we've done a good bit of applications, not with Pyrawall necessarily, but with our ArmorMax system, which uses the same PYRAMAT, not for true coastal applications, on the ocean front, but on intercoastal, so ponds and lake banks. There's a limitation there. We to date don't have a Pyrawall installation directly on a coastline that's in a saltwater environment. There's not an issue from a corrosion perspective, but depending on the severity of the storm events, there could be a limitation there. But it's to be determined at this point. There's a lot that goes into that, and it's a huge opportunity for coastline applications, but there's not a whole lot of information, not a whole lot of successful solutions out there in the market. Yeah, we're always looking for pilot projects if you have any ideas. Next question is similar but a little different perspective. Is there any experience with shoreline or bank animal attacks? So nesting. So I guess there's two perspectives. I guess it's one, if you want animals to be able to nest, or if you want it to be able to resist nesting so that it doesn't reduce the durability or provide any instability. I'll just answer it from the stability perspective. Again, with the PYRAMAT being the base material, we've had a lot of success with PYRAMAT being what we call a deterrent for burrowing animals. There's a lot of testing that was done for the Army Corps of Engineers for all the work they've done in the levees of New Orleans to deter things like feral hogs from burrowing into the levee banks. And what they found is something like PYRAMAT, while if a hog really wants to, it can get through it. It very much so deters them and encourages them to go somewhere else because it's that durable. It takes a lot of time and effort. We've seen that also in California, where small burrowing animals go elsewhere because they would rather not put the effort into digging through the PYRAMAT. So it's definitely a deterrent for burrowing animals. Again, that's a benefit if the question is for maintaining stability of your bank. Next one, we talked about the PowerPoint presentation already. So again, if you can give information or help us understand what information you're looking for, we can give you more direction on content. Fire resistance and degradation, that's a good question and a long answer. But in short, polypropylene itself in general will, before it burns, it will melt and pull back. We've had multiple applications, some in Texas, some in the Carolinas, where after PYRAMAT was installed, a natural fire happened. And what we've seen is that the PYRAMAT actually performed very well and wasn't severely damaged. But when fire did happen around it, it's not a fuel for the fire, but will pull away before it catches on fire. And so a lot of times it puts itself out. In terms of durability or degradation, that's always a concern. With vegetation burning, if you have a large enough wildfire, it'll burn enough to have an issue. But that's really mostly an issue on most of those construction materials as well. We're as always, we have a lot of research and development going on, and so that's always a question that's we're looking for an answer for.
I'll just chip in here again. As long as the vegetation is fairly low growing, even in the dry time of the summer when this vegetation may be dormant, the chances are a wildfire is going to move through such an area fairly quickly. So it's not like the PYRAMAT's going to be exposed to that heat for several hours. It may be exposed for 15 or 20 minutes and the fire moves on. So in that regard, you know, it's obviously it is sensitive to fire, but it's not going to be exposed to fire for that long if the proper vegetation cover is in place on the Pyrawall.
And in terms of thinking about it too, while the facing material can be directly exposed, the reinforcement in the back of it, even the PYRAMAT as it extends into the soil, is not exposed. And what we found is there's research that shows that if you essentially have 2 to 3 inches of soil covering a material, the temperatures get so low below that 2 to 3 inches that essentially they won't ignite. That temperature gets reduced pretty quickly as that soil layer comes there. So that while you might have some superficial damage, the structural integrity should be maintained. Next question is asking about a cost estimate. It depends. Obviously, it's regional in terms of where the material is installed. We've had it installed anywhere from $30 a square foot of face up to $50 or $60 a square foot of face. It just depends on the access. Stan mentioned the Kaneohe project. There wasn't really no access, so that was a more expensive installation just due to the access and the lack of ability to get machinery in there. But I would say it's generally we compete very well with typical retaining wall structures, modular block walls. We again very competitive with those, as well as having our advantages as well from the environmental and the durability perspective. Next question is, it was mentioned that the material used to come in black and now it comes in green and tan. Would it be available in different colors like dark brown? Right now, no. We can always look into that. From a manufacturing perspective, it's about amount of material, volumes, and consistency. We can make any color we want, but there's a balance because in developing a new color, you also have to develop the antioxidant packages that's going to control the degradation from the UV perspective, and that's a very complex process. So it can be done, but at this point, the only 2 colors we offer are green and tan. And the tan it's a good-looking tan. It blends in with the most unvegetated applications. Next question: on a slope subjected to vigorous wave, wake, wash, would you expect migration of fines or loss in backfill? I would if you're using fine soil in that application. So as I mentioned before, if we are having a more of a shoreline application that has wave impact at some point, or it's on a pond bank or something, I would suggest in that area where the waves, the tidal fluctuation or just the fluctuation water level is going to be there, that we use a backfill that's more of a granular fill, such as like a 57 stone or something that won't be as sensitive to that migration of fines. Next question: how does it stand up to tidal conditions where groundwater fluctuations on both sides of the face along with tide? Again, similar answer. As long as you use the right infill material, I think that there should be no issue with poor water pressure buildup or migration of fines as well.
And because you're constructing these lifts one at a time, you can change the backfill as you go up in the wall. I mean, you can have coarser material in the first couple of lifts. You can go to a finer grain material in the middle of the wall and then actually go to a more of a topsoil type material in the upper portion of the wall. So it's up to the designer working, in conjunction with the client to basically fill these walls however you want them filled.
Next question: what was the largest diameter plant that can be used with the product? Again, as I mentioned before, with vegetation, it can be established naturally with trees and shrubs growing as they will, or we've gone through and actually planted in shrubs where you can, with the PYRAMAT material, place it in during the construction process. I've seen up to 6 or 7 inch diameter plants growing through the material and uninhibited, and that was just several years after installation. So there is no, it doesn't limit the vegetation establishment and the type of vegetation. It's pretty varying.
However, during construction, if you're going to be sprigging in live root stock or laying cuttings in between the lifts, I mean, you're not going to want to put in, 3 or 4 inch diameter material here. You're going to be wanting to use cuttings that are, I'd say, 1/2 inch or smaller in diameter, initially when installed.
So next question is, has Pyrawall been used along the East Coast? And if so, where? Right now, we have some use them on the East Coast, but not the actual coast, if that was your specific question. So we've used it within the Cincinnati area here recently, and we have several applications, projects in design up along the states along the east of the U.S. Next question was, is there any cases of Pyrawall in seismic zones? To date, no, but we have the ability to incorporate that component in the design perspective. Was that?
I was just going to add that this project in Washington State, we did do a seismic design on that. It's not a highly active seismic zone, but there was a seismic coefficient of, I think, a horizontal seismic coefficient of 0.07 that was used to design that embankment in Washington State. So we have the capability to include seismic into the geotechnical analysis. And of course, we'd love to get a wall put in somewhere in the Wasatch area in Utah, or maybe in California somewhere, because these walls are flexible. They've got a lot of give. All the prognostications are that these will perform well during a seismic event.
Next question was the anchors. So what anchors the geogrid at the face to prevent pullout? Again, this is a really composite system that uses the Pyrawall and potentially primary reinforcement for the geogrid. And the way it works is that with the Pyrawall itself, the wrapping is embedded around 4 feet or so into the wall face. The primary reinforcement is sandwiched between the Pyrawall lifts, and you have about 1 inch of soil between each side, so that it's not a geogrid on PYRAMAT interface. It's interacting within the soil, and that 3 to 4 feet of interaction is enough to resist pullout at the face. Next question: which, if any, state highway departments specified a Pyrawall-like product? So to be honest, Pyrawall is a very new system. There are similar vegetated wall systems out there. I'm not sure that all the states work or have these vegetated systems in their APL or QPL process. Right now, Pyrawall, with it being new, we don't really have many projects with state highways, state DOTs. We have a few in the works right now, but we haven't had any specifically with them that's required to be on their lists at this point. The question was, what's Stan's last name? Stan Miller. That's an easy one. I got that. Again, the question of what's the approximate cost. Again, it depends. We've seen it for anywhere from $30 a square foot of face material and installation completed bid item up to $50 to $60 a square foot of face. But typically, again, it's a competitive system that we've had situations where we are more economical than typical block retaining wall systems. It just depends on the scale of the project and the location and access as well. Can Pyrawall be designed in submerged condition? I would say it can. One of the questions that has come up is constructability. So being able to build it underwater versus being able to build it and let water then rise. I would say the ideal situation is being able to build it in the dry and then let the water rise as it fluctuates throughout the year. I'm not saying that it couldn't be built underwater. Yeah, you might need to be a little bit more creative on that installation process. Again, the question about brush fires came up again. So yes, so just to reiterate, typically with the PYRAMAT, vegetation helps when it does catch on fire. When the vegetation does have a fire, the PYRAMAT, being made of polypropylene, typically doesn't catch on fire, but will draw away and melt from that fire and put itself out. And in addition, once you get 2 to 3 inches below the soil, the temperature reduces so much to where fire is not really a possibility at that point. How is a damaged face restored? So what I would suggest is typically what we'll do is we can patch a section. So the thing that's good about the PYRAMAT is it's a very dimensionally stable and very durable material, so that if damage does occur, it doesn't propagate, it doesn't expose more material. We have a couple of different ideas on how to patch sections. Typically what we're looking at is if it's in an area where we can access it well, we'd replace that section of the lift. But if it's, say, at the bottom of a lift, we would potentially look at using a patch of the HPTRM along with earth anchors to tie that system together, so that you don't have to come and take out 6 or 7 lifts of wall just to get back in there. Having a superficial face would essentially fix the issue there. Let's see here, hold on. Do we need to consider installation damage or chemical durability reduction factors in selecting a grade of PYRAMAT? From the installation perspective, so the question is, for a long-term design strength value, typically you look at various factors such as creep, installation damage, chemical or biological degradation. Those 3 are the main ones for potential reduction in your tensile strength. Chemical degradation, again, because the PYRAMAT is a very durable material that's really designed to be exposed, you essentially will not have reduction in tensile strength for the chemical degradation. Additionally, with it being a very durable material, you don't have very much installation damage. If you come back and you say you put guardrails in or something that's going to puncture that material, that's a different question. But typically, the value we use for PYRAMAT is pretty conservative, anywhere from, say, 300 to 500 pounds per foot, with some pretty conservative reduction values on the tensile strength. So again, we can look at specific scenarios just to make sure that we're being appropriately conservative as we need to.
Are they asking about grades of PYRAMAT, like PYRAMAT 50, PYRAMAT 75?
That's a good question. So yeah, if it is with respects to the type of PYRAMAT, so for those you don't know, PYRAMAT is the brand we use, but you have PYRAMAT 25, you have PYRAMAT 50, and you have PYRAMAT 75. For Pyrawall, we're really only going to use the PYRAMAT 75 due to the thickness and the long-term durability. The thickness is really needed to interface well with the internal bracing and those structures there. So PYRAMAT 75 is, if that is the question, PYRAMAT 75 is really the only material that we're going to use with the Pyrawall system at this point. So that was a lot of very good questions. If you guys have more, obviously, feel free to either submit them or reach out to us later. Again, my name is Drew Loazo. I'm the Engineering Services Manager at ProPEX. With that, I guess we'll hand it over to you, Beth.
All right, thank you so much. Yeah, that was a phenomenal Q&A that you guys had. Dan, Drew, and Stan, if you don't mind sharing, go ahead and share your email with the audience. I've had a lot of inquiries about your personal contact information, how they can reach out to you.
Okay, just to be clear, can I put that on the chat and that'll be good?
Yeah, absolutely. Put that on the chat and you guys can get it there. Also, I just wanted to make it clear, I don't think I said this in the introduction. There are 3 handouts in the handout tab section, along with the multiple viewer form and the certificate of completion. That makes a total of 5 handouts. You definitely want to go ahead and grab your certificate of completion while this webinar is still up and running. Otherwise, you'll have to personally reach out to me, and that could take a few days to acquire that. So while we're on and talking, go ahead, go to the handout section, download your PDFs that you need. In addition to, I also wanted to make it clear that all the questions that were asked today, they will have answers provided in the next week at csengineermag.com/continuing education. If you go to the archived webinar of this, you will be able to see a complete spreadsheet of the Q&A. And I think that about sums it up. I appreciate you both so much for your time, and the audience as well.
We were glad to do it. Thank you, Beth.
Thank you. Everyone have a good day.